Ladies and gentlemen, welcome to the first plenary session of CLEO 2016.
It was what we call a chirp, and it was strong.
Everybody thought it was a fluke. It was too good.
And I thought, my God, this looks like it's it.
Oh my gosh, this is real. It took us 25 years and 2 detectors to finally detect a gravitational wave. We have interferometers, one in Hanford, Washington, one in Livingston, Louisiana, to detect the stretching and compressing of space.
We literally look for changes in the space-time distance in our instruments as the gravitational wave goes by.
And the gravitational wave pushes them together and apart by 1/1000th the diameter of the nucleus of an atom. No wonder it's taken so long to pull this off.
However, what's even more remarkable about this is what we detected.
We have observed gravitational waves from 2 black holes forming a larger black hole.
For the first time, 2 black holes
Spiraling together, coalescing, merging, creating wild oscillations. A storm in the fabric of space and time.
Please join me in welcoming our plenary speaker, Dr. David Wright.
I am delighted and honored to be speaking to everyone here tonight about really what I think is a phenomenal discovery that happened actually in September of last year. And I want to point out that everything I'm talking about really represents the work of a large number of people. So I'm just lucky enough to be here representing it. So this picture, can we get the, yes, thank you. All right, so this picture that you see on my view graph here, you saw a video of that. I'm going to come back to that video a little later on because it talks about exactly what we did when we made this discovery. Let me start with a 1-slide lecture on general relativity. So this is all you need to know about general relativity if you want to be a gravitational wave physicist. It starts with something called the Einstein field equations. That's the equations that are in the upper left-hand side there. And it's a tensorial theory. It's a beautiful, mathematically elegant theory. It's a theory of geometry. And basically what it says, what Einstein's inspiration was and what he was able to encode mathematically is that space and time, and that's that g mu nu on the left-hand side of the equation, is equal to matter and energy, all right, that they're fundamentally equivalent, all right, and that's on the right-hand side of the equation. And the way to think about that equation is that matter, mass energy, tells space how to curve, and space tells matter how to move, all right? So this replaced the Newtonian theory of gravity. Now you can play some tricks and some simplifications to get a wave equation out of it. So if you assume that you're in flat space-time, that's the space-time that we live in, Minkowskian, sort of Euclidean plus time, and then you also say there's a weak perturbation on the metric. The metric is the thing that's used to actually measure distances in general relativity. You come up with that equation in the lower left-hand corner, which I think everybody here recognizes as a wave equation, for that metric component h mu nu. All right, and so that's what a gravitational wave is. But the thing that's really tough about gravity, and the thing that's tough about this measurement, and why it's taken so long, is that coupling constant, that constant that sits between g mu nu and t mu nu is very tiny. It's about 10 to the minus 43. So this effectively means that it takes a huge amount of mass to make an appreciable dent or an appreciable warp in space-time. Okay, now you solve the wave equation, you get a propagating exponential wave. Simple, everybody knows that. Physically, what you're measuring, what that h is a strain. It's a change in length per unit length, which those 2 cartoons that are oscillating there give you the 2 polarizations. So if a gravitational wave is coming out of the board at you, all right, on one cycle, your hands would be, the fingers on your hands would be moving apart, they'd be coming together, and alternatively at the same time, in the other direction, they'd be going oppositely. So out like this, in like this. And because it's a strain, the further away you go, all right, the more the displacement that you'll see. That's the delta L over L, which immediately suggests that if you want to detect gravitational waves, you want big interferometers, all right? And it also means you have to detect displacements that are awful small. And just to give you a sense of that, so the equation h mu nu, that's basically the gravitational waves are not sourced like in electromagnetic radiation by dipole sources. They're sourced by quadrupole mass distributions, time-dependent quadrupole mass distributions. And again, there's that darn factor of g over c to the fourth, which means that for really massive objects or objects that have massive quadrupole mass moments, you're still stuck with a small number. And for these two black holes, for example, that we saw merging back in September, that number, when you put in the numbers for the black holes, 30 solar masses, spinning around at about 200 hertz, the number's 10 to the minus 21, which if you're an experimentalist, that's a dauntingly small number, but it can be detected. All right, so why are gravitational waves important? Why have we been looking for them for so long? Why has it taken 40 years, and why do we continue to do it? The reason is because they answer questions in fundamental physics and astrophysics and cosmology that you can't get from any other source. All right, and that's due to the unique nature of the gravitational field. It probes mass motion, coherent bulk mass motion, as opposed to electromagnetic astronomy, which looks mostly at charge motion. Okay, so I won't go through the list of questions here. You can read them for yourself. I'll point out a few that this first detection actually answered. So first of all, is general relativity the correct theory of gravity? If we see gravitational waves that don't look like general relativity, that would be quite exciting. Turns out that that wasn't the case here. Are black holes truly bald? What does that mean? There's a theorem that says that black holes have no hair. Hair in this case is any extraneous information except for charge, mass, and angular momentum. And in fact, astrophysical black holes don't have charge. They only have mass and angular momentum. How many of them are there in the universe? So even with this one detection that we made back in September, we're starting to get answers to these kinds of questions. There are other interesting questions that one can pose too. One of the most interesting and really tough for LIGO to get at is the nature of the Big Bang. So if you could see gravitational waves from the primordial universe, you'd be able to know more about the nature of the Big Bang and the beginnings of the universe than you could from all the electromagnetic astronomy combined. And that's simply because electromagnetic astronomy can't look back for more than about 400,000 years after the birth of the universe, after the Big Bang. Just the nature of the ionization of the universe at the time. So these are all great fundamental questions that we hope we're going to be able to answer over the next few years. So how do we do it? So let me walk you through, this is sort of a very cartoon idea of the way LIGO works, but I think it gets the impression across. So we use Michelson interferometry. It's interesting that, you know, Michelson and Morley were the experimentalists who really got special relativity on the map. Well, this is an extension of that. We use an enhancement, I would call it an Michelson-Morley interferometer on steroids, all right? With a trick. We have to play a trick, and the trick we have to play is we have to keep the mirrors, all right, freely falling. In other words, we have to make sure that the only forces that they experience, or the dominant forces that they experience, are from a passing gravitational wave, and we do that by suspending the mirrors. All right, so what happens is a gravitational wave passes over the interferometer. It alternatively stretches and compresses one arm of the interferometer while it alternatively compresses and stretches the other arm. And it does this over a full cycle, as that cartoon on the bottom shows there. And so what you do is you configure your interferometer in such a way that when there's no gravitational wave present, there's very little light going to the photodetector. That's that sort of cone-shaped object there. But when a gravitational wave passes, it does that stretching and compressing, again, very tiny amount. The strain, as I said, is about 10 to the minus 21 or 10 to the minus 22. And it leads to basically a time-dependent signal. And so what, in essence, the interferometer is doing is it's transducing space-time into photocurrent. So it's taking these gravitational waves, which have a huge amount of energy in them, even though their amplitude isn't very large, and it's stretching and compressing space-time. What it basically is doing is changing the time delay that a photon experiences as it leaves the beam splitter and goes down one arm as opposed to the other arm. When it comes back, because the time delays are different, there's a change in the interference pattern. And so we're transducing that. Okay, so that's the basic idea. As you saw in the video, there are two interferometers. One is in Livingston, Louisiana, near Baton Rouge. The other is in Hanford, Washington. The reason there are two is because there are a lot of ways that our environment and even the components of the interferometers themselves can actually fool you into thinking that you're seeing a gravitational wave. So in order to confirm that you've actually seen a gravitational wave, you have to see it not on just one detector, but on both detectors, with a time delay commensurate with the time difference between the two detectors. So one of the things I should have said earlier is that these gravitational waves, if we believe Einstein, are expected to travel at the speed of light. All right, so that's an important discriminator for us here. And I'll point out that I'm at Caltech. There's a group at MIT. There's a whole group of scientists at the Hanford Observatory and at the Livingston Observatory who actually operate and commission the detectors, keep them working, improve them, make them better. And then there's a much larger group of people, the LIGO scientific collaboration, about 1,000 people that actually do a lot of the work. This is big science, and you need a lot of people to do it. All right, so there's a picture. I love this picture of, this is a picture of Hanford, and you get a sense of scale here. That corner station building, you might be able to see a car there. Those beam tube enclosures that you see are 4 kilometers long, and of course there are 2 of them. If you go to Livingston, Louisiana, you see the same thing, only you can tell it's Livingston because you're more in a swamp than you are in a desert. All right, now let me come to the heart of LIGO and why, what makes it so hard. So this is a plot that's going to get shown a couple more times in my talk, so I should walk you through it. So on the x-axis is frequency, from about 10 hertz, a little bit less, to a little bit more than a kilohertz. And that's really the bandwidth with which LIGO operates. All right, so that's the frequency range in which we're sensitive to gravitational wave sources. On the y-axis is strain, all right, but not delta L over L, but in unit, basically amplitude spectral density per square root hertz. And in order to understand how you would make a gravitational wave detector and make it sensitive enough to be able to detect those 10 to the minus 21 or 10 to the minus 22 changes in strain, you have to understand all the noises that come in, and then you have to design your interferometer to overcome them or combat them. All right, and they come in two flavors, actually 3 flavors. One is displacement noises. So I said the mirrors are hanging, they're in free fall, all right? So you want to make sure that no forces, no other forces act to accelerate those mirrors, that the only force that's acting to accelerate those mirrors is the passing the dynamic gravitational wave field that's passing over the interferometer. All right, that's all well and good, but there are lots of other forces that are actually working to make your life tough. The first one is seismic noise. The fact that we live on the Earth, the fact that the Earth is the ground moves, it actually moves at low frequencies with an amplitude of about a micron. All right, and we're trying to detect displacements. Now, instead of strain, I'll talk in displacements of about 10 to the minus 18 or 10 to the minus 19 meters. We have to roll that noise off, all right, over basically a factor of 1 trillion or 10 trillion. All right, and that curve that you see there is it looks like it's the brown curve, if my colors are right there. Okay, so you have to do that. So we design very sophisticated seismic isolation systems and suspensions to do that. There's also radiation pressure noise. All right, this is a really interesting one. It comes about from the fundamental nature of light. Photons carry momentum, all right, and so when they hit something, they can impart a force to it, an impulse to it. The photons also come in random times due to the quantum nature of light. So the photons are sort of randomly hitting the mirrors inside the interferometer, and they're buffeting the mirrors around. So that's a source of noise, all right? There's also thermal noise. This is actually a real big one for us. It's a real problem, and we're still trying to tackle it to make even better detectors. Thermal noise is the fact that everything in our detector is at a finite temperature. Statistical mechanics tells you that anything at a finite temperature, all right, has energy in it, and anything that has energy in it moves, all right? And so because our mirrors are at room temperature, the surface of those mirrors is actually moving, and it's moving with an amplitude of about 10 to the minus 20 meters, all right? And we work very hard to use, and I'll talk a little bit about the mirrors later, to use very, very pure fused silica mirrors so that we confine the motion, right? The spectral motion of that displacement into a region where we don't care about it, where it's far, far away from the detection band inside that curve that I show you there. All right, it turns out, again, that the mirrors are suspended, and that's to get them acting like freely falling mirrors. But the suspensions themselves vibrate. They have energy in them, and they're under stress. And they vibrate, and so there's a component of the motion, thermal noise component due to the suspensions. And it turns out the mirror coatings themselves actually are really probably the biggest source of it. Okay, so those are displacement noises. Then there's also sensing noises, all right, what the phase that the photodetector sees, all right? And we, of course, measure amplitude, but we do it using interferometry, so we're sensitive to the phase of the light that recombines at the beam splitter. All right, so there's shot noise. This is the other side of radiation pressure noise. The fact that photons are arriving at random times means that leads to sort of a time-dependent phase noise in your measurement. And there's also residual gas. If we were doing this in a place where there was no gas at all, say in deep space, the photons would go and they wouldn't scatter at all. They'd go down the end of the interferometer and come back and everything would be great. But we on Earth live in an atmosphere, so we have to put a vacuum system in, and we pump our vacuum down to about 10 to the minus 8, 10 to the minus 9 torr, and that limits the amount of scattering that photons undergo when they hit molecules inside the vacuum system, because if they scatter off it, that changes their phase. All right, and then buried underneath all that are technical noises, and there are loads of them. There are no control noises from the fact that we have to sense the position of the mirrors and hold them together. The laser itself has noise. It has amplitude fluctuations, RIN. It has frequency fluctuations. The beam points around. And these are just one of probably 50 other noise sources that you have to understand and try and sort of beat as you build your interferometer. And that's really the challenge with this. Anyway, that's the design curve that we had for advanced LIGO. And you can see that we're limited really at low frequency by seismic noise and this radiation pressure noise. At high frequency, we're limited by what we call shot noise. And people who know shot noise will tell me that it's white. And I will agree, it's white noise, frequency independent. I'll agree with you, but then we have Fabry-Perot cavities, and so they act as low-pass filters, and that's why it rolls up at high frequencies. And then in the mid-band, in this region around 100 hertz, which is really our most sensitive region, 100 to a few hundred hertz, it's the thermal noise, in particular the coating thermal noise that I told you about. So anyway, so how do we beat all that? So this is just a quick walkthrough through the interferometer. We start with a laser, and I'll say more about the laser in slides, so I won't say anything about it now. The interferometer components you see there, this is again sort of a slightly dumbed down version of the interferometer, but it gives you the basic idea. We start with a laser, we go through phase modulators to put sidebands on the beam. Those are used for basically RF sidebands for signal control, for heterodyne measurements. There's a mode cleaner, which is a filter cavity. It basically cleans up the amplitude, frequency, and spatial mode quality of the beam. Go through a Faraday isolator. Go into the interferometer. The interferometer, you'll see that you'll recognize the beam splitter and the end mirrors. We use Fabry-Perot arm cavities Fabry-Perots in the arms, and that actually allows us to effectively enhance the phase gain. It makes the light storage time in the interferometer a lot longer, in our case by about a factor of 200. So that makes the interferometer appear like it's 200 times longer. Alternatively, it makes it, which means it senses more of the gravitational wave as it passes. Alternatively, it amplifies the phase shift that you get for a unit displacement of the test masses relative to the beam splitter. There are power recycling and signal recycling cavities. The signal recycling cavities on the input side, that's that little Z there. That allows us to actually sort of passively amplify the laser power further. So we start with a laser that's about 200 watts. We get it up to about 4 kilowatts inside the recycling cavity. And then on the output side, that sort of N-shaped optical configuration is a signal recycling cavity. And that, again, allows us to enhance the amount of phase shift that we get from the passing gravitational wave. And then there's something called an output mode cleaner there. All right, so in order to make that all work, we have to put in seismic isolation systems. So these seismic isolation systems are active. They sense the ground motion. They feed back to stages above where the sensors are to correct for that, and then we do that again, so it's a dual stage thing. So the analogy that I give when I give public talks is it's a little bit like if you drive a Mercedes-Benz and you're driving over a cobblestone street, if you're in the car, you really don't feel the motion at all because the Mercedes-Benz suspension control is sensing it and then feeding it back. Well, we do that, but we do it thousands of times better. All right. We then also we have mirrors that are 40 kilograms in mass. Heavier mirrors make less of effect for photon buffeting. That's why you want heavy mirrors. And they're suspended by 4 optical fibers, and then there's even upper level suspension, so they're suspended 4 times. And we use the fact that a suspension is a harmonic oscillator and it acts as a filter. So four suspension gives you f to the 8th roll-off in noise. All right. There's basically auxiliary lasers that we use to lock the cavities. And there's a lot of stuff that I'm not showing here because I don't have time. But you get a sense of the complexity of this. And there's, again, not one of these, but there's 2 of these. So let me talk a little bit about the laser. I think this might be interesting to this crowd. So this was designed by a group at the Albert Einstein Institute in Hanover, Germany. It's built by Laserzentrum Hanover and actually also in collaboration with scientists in LIGO. It's, by some standards, a pretty generic laser. It's a neodymium YAG laser, 3 stages, 180 watts. All right, that doesn't sound so impressive until you realize that it has to be ultra-stabilized. So the power noise is 10 to the minus 7. Per root hertz at 10 hertz. That takes a lot of effort to get to. And the frequency noise is 0.1 hertz per root hertz. And that's just the raw laser. We then put added frequency stabilization to get to the level that we need for LIGO. Anyway, it's a nice laser. It's completely in a clean room at these power levels. Dust is an anathema, so you have to worry about that. Let me come to what I think are really the crown jewels of LIGO, and that's the mirrors themselves, the test masses. So these are made of ultra-pure fused silica, the same kind of fused silica that you find in optical fibers that carry telecom across the country. But they're big. They're these 40-kilogram mirrors. They're 340 millimeters in diameter. 200 millimeters thick, so they're very heavy, 40 kilograms. They're not easy to carry around. And they're exquisitely polished, and actually this was one of the things that we had to work hard on, was to find a way to basically, how do you make a perfect sphere, all right, for these mirrors? And by perfect sphere, I mean that they don't deviate from a sphere to within maybe a little bit more than an angstrom. All right, and it turns out you can do that with combinations of super polish and ion beam milling. It was really a tour de force by the companies that we worked with to do that. And then at the end, you have to coat the mirrors. And coating the mirrors turned out to be one of the biggest challenges in getting LIGO to work. And that's because it's just really hard. So the optical coatings are tantalum pentoxide and fused silica, SiO2. And they're quarter wave stacks. They have to be basically uniform to a level of about 10 to the minus 3, and their coating thickness is only maybe 10 microns. They have to be ultra low absorption. As you can see in the plots there, these mirrors have absorptions of about a half a part per million, and that's because there's a lot of power stored in the cavity. During the initial LIGO run, there's about 100 kilowatts of average power stored in the cavity, so you don't want that to absorb and cause the mirrors to distort. All right. The coatings themselves also have to preserve the surface figure, and there's a beautiful plot there of one of the challenges that we encountered with the coatings. And you see that spirograph pattern, that spiral pattern there. And if you look carefully at the scale, you see that spirograph pattern only deviates by about a few nanometers. So this is still lambda by 300 or lambda by 400 at these wavelengths. But that's enough to actually scatter light out of the cavity. So it turns out that's a diffraction grating. And we were able to manage it. We actually, the mirrors that we used actually looked a little bit better than this. But I wanted to show this because I think it's a good example of how hard it is to do this kind of optical fabrication. All right, so you put that all together. And again, I'm skipping a lot of the details. And here's what we got in our first run. All right, so again, this is the plot showing frequency against now displacement sensitivity. So you get an idea of how much we're measuring these displacements. And you can see that in the most sensitive region, we're below 10 to the minus 19 meters per root hertz. All those other curves there are basically some of the noises that I've talked about before. And the one I want you to pay attention to is the gray curve, other degree of freedom. All right, the other degree of freedom curve is all the other noises rolled up and projected here. And the way, by the way, that you calculate these things is they're all uncorrelated, so you just do a quadrature sum of them. But what you should pay attention to is that if you add up all of the theoretical curves in that other degree of freedom curve there, and then you compare it to the red curve, you'll see that they don't quite agree, and there's a deficit, we'll call it a budget deficit, noise budget deficit between about 30 hertz and about 80 or 100 hertz. And we're trying to understand where that is now. And that's really important, that low frequency noise is really something that we want to improve. Anyway, this was good enough for us to decide to start running advanced LIGO. So construction completed in 2014, and we commissioned our interferometers to make them this sensitive. And we got operating. We started running in September of 2015. Now, I want to take a moment to tell you some of the interesting physics that you encounter with these interferometers. All right, and the first is something that I think this group will be familiar with. It's basically a nonlinear optomechanical or acousto-mechanical interaction. We call it a parametric instability. It was first found by a group in Moscow State led by Vladimir Briginsky, who theorized it. But what basically happens here is if you have a mirror that's at a finite temperature, all right, it's thermally excited, and the thermal excitations, of course, leads to different kinds of motions on the surface of the mirror. It's just natural statistical mechanics. You have a laser field that is inside the cavity that is sensing those motions, all right, and those motions scatter light out of the fundamental TEM00 Gaussian mode and into higher order modes. And of course, that's a process that feeds back on itself. So the arm cavity field drives these modes, which then scatters more light into the modes, which then further drives the modes, and it builds up. And this is called parametric gain. The equation tells you what you're up against. Basically, because we use very high Q, very high quality factor mirrors, we're susceptible to this. We use massive mirrors, that helps us a little bit. And then there's something called the optical mode gain. And you can see the picture on the lower right shows you the optical mode inside the interferometer that interacts. And actually the mode overlap, the mode integral overlap there is only about 0.1 or 0.15. But it's enough to drive an instability. And the acoustic mode in this case is outside our band. It's at 15 kilohertz. But unfortunately, it's enough to cause us problems. And we discovered this when we were doing commissioning, sort of getting the interferometers working properly. And you can see, all right, where if you look at the photodiode on the output port and you look at the right frequency, and actually in our case they're aliased down, but if you look at the right frequency, you'll see that this thing builds up exponentially. And if you let it run away, it basically breaks the interferometer in the sense that the interferometer cavity can no longer be stable and locked. All right, and this happened at 50 kilowatts. So we have a problem. And the problem is how do you damp that mode out? How do you squelch it? How do you quench it? How do you get rid of it? And it turns out you can do that very easily by changing the radius of curvature of the mirrors. And we do that by we have ring cavities, ring heaters that actually deposit heat on the mirror. And by depositing heat on the outer edge of the mirror, they don't contact the mirror, but they radiate. All right, you're able to change the radius of curvature. And changing the radius of curvature just shifts the mode frequency of the acoustic mode outside of the optical mode spectrum of the Fabry-Perot cavity such that it goes away. And so we demonstrated that we could do that. Turns out when you go up to 100 kilowatts, you start to see more modes. We're going to see more of these. So there are different ways of attacking these. The radius of curvature tuning has worked. We have ideas for using basically electrostatic feedback. We can do that to our mirrors. That's been tested. It seems to work. Ultimately, we may actually have to go in and put little plungers on our mirrors that actually selectively suck the energy out of these parametric modes. So we'll see how that goes over the next few years. All right, so now let me come to the discovery. The reason I'm here is because on September 14th, 2015, an event came into our detectors. Let me start by saying that I've given a lot of LIGO talks over my career, and I would give these talks, especially during initial LIGO, which ran from about 2002 to 2010. And I would go, I'd be asked, well, what have you discovered? And I'd say, nothing. And I'd show this slide. And then I'd go, but we published some really nice papers. Look, we've got some PRLs, we've got some astrophysical journals, we've got a new journal of physics, we've got a Nature of Physics, we've got a Nature of Photonics, we've even got a Nature paper. But we hadn't discovered anything. And I think that's just because nature hadn't been kind enough to us in initial LIGO. But nature became very kind to us on September 14th. We hadn't even started operating our detectors. We were going to start running on September 18th, all right? So we were doing some testing. We were checking the calibrations. We were making sure that we could pass information from our detectors. But we were very smart and a little bit lucky. We were smart in that even though we weren't running, we kept our detectors operating in a science mode. In other words, they were taking science quality data. And the morning of September 14th, this came in very late at night, I woke up in my office and I was hit with this. All right, so what you are hearing and listening to there is basically the signal that came into our interferometers. And it's shown in two ways. It's shown as a time series. You can see the Hanford and Livingston time series. And if your eyes are very careful, you can see there's a little bit of a shift. Livingston saw the signal about 7 milliseconds before Hanford did. And if you want to go in the spectral dimension, you can plot it as a spectrogram, and that's what those two curves are there. And it's actually a signal that has a very characteristic frequency behavior. It's called a chirp. It sweeps up in frequency, and that's because of the orbital nature of these black holes that we discovered as they're inspiraling and merging together. I'm going to play it again. Let me see if I can go back. Yeah, good. So you can hear the thump. All right, so that data that you hear is basically the data that comes out of the photodiode. It's been a little bit filtered. We bandpass filter it from, I think, 30 hertz to about 300 hertz. We notch out some lines in there. But it's really the raw data. And that actually says something about this signal. This was a really big signal. This was a whopper, and that's quite great. That thump that you heard was, in fact, the thump that came from basically those two black holes colliding with one another. All right, they didn't make that sound, but that's what they put on our photodiodes, and then we digitized it. I want to play it, I want to shift it up 400 hertz so you can really get a sense of this chirp here. So, all right, so you hear that whip, 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 and that's very interesting. Now, there's a huge amount of information that's contained in those two waveforms. All right, so there's the data again. This is figure 1 of our PhysRev letter paper that came out on February 11th. There's the data from Hanford, Washington, and Louisiana, and you can see the data overlaid and shifted. So the data in the upper right-hand plot basically shows how consistent this is. So this is really quite a spectacular signal. It has all the right characteristics. The frequency is chirped. In other words, it starts at lower frequencies and goes to higher frequencies. The amplitudes are relatively consistent given the differences in the detector and the location on the sky of the event. It's completely consistent with numerical relativity simulations of these binary black holes merging. If you subtract off the signal that you predict from the numerical relativity simulations, you get background noise. All right, so everything about this signal is right. All right, we heard it on September 14th. It took us 5 months to actually go public with it, and that's because we wanted to be very, very careful. All right, that you can't make an announcement like this without checking everything, and so we checked everything. Let me point out that the actual displacement, you can calculate the displacement from that strain, and it's 4 times 10 to the minus 18 meters. So these two huge black holes, all right, basically produced a signal in our detector that was 4 times 10 to the minus 18 meters. So that gives you a sense of scale here. I want to show the movie now. So the movie that you're going to see is a simulation that was taken from those waveforms that I just showed you. All right, solving the equations of general relativity on a computer, something called numerical relativity. There are 2 black holes in this particular event. One, the big guy, is 36 solar masses. It's about 200 kilometers in diameter. The small guy littler guy, is almost 30 solar masses, about 155 kilometers in diameter. So you're looking at this very up close and personal, and the simulation is slowed down by about 100 times. And again, this is a real simulation using numerical relativity. The stars that you see behind it are actually, they're just there so your eye can calibrate the motion of the black holes. And by the way, the black things that you see are event horizons, all right? You can't actually see into the black hole. All right, so I'm going to start the movie, and you see these two black holes are orbiting around one another, all right? And they're orbiting slowly, and they're basically warping space-time in such a way that the star fields behind them, the light that passes through, gets bent. And that's what you see, those two rings there are sort of called, or they are called Einstein rings. All right, you can see they're getting closer together, the frequency's picking up a little bit, they're getting a little bit faster, and then eventually, wham, they collide. And you see that little vibration that happens at the end. That little vibration that you see, all right, is actually the burst of the gravitational wave energy that came out there. All right, this was a remarkable event in a number of ways. First, no one had ever seen two black holes merging to form a new black hole. And that's not unexpected because black holes are not emitters of electromagnetic radiation. So really the only way to see this signal, we believe the only way to see this signal is using LIGO and gravitational waves. The source parameters I think are fascinating. So 36 on 29 solar masses. These particular masses are heavier stellar mass black holes than have ever been observed before through conventional X-ray binary. You're looking at X-ray binaries with black holes in them. So this sort of stunned the astrophysics community. The final black hole had spin, all right, of about 0.67. That's a normalized spin. To put that in perspective, if this were 1, the event horizon of that black hole would be spinning at the speed of light. How far away were they? They were about 410 megaparsecs, and I'll point out that all these numbers have large error bars on them. 410 megaparsecs is about 1.3 billion light years. So this signal started about 1.3 billion light years ago and passed through the Earth. It actually did come through the Earth before it hit our detectors, and we just were lucky enough to be on when it happened. Radiated energy was 3 solar masses. So if you do the final mass, you look at the final mass, 62 solar masses. The initial masses summed to about 65 solar masses. The difference is what was radiated in gravitational waves, and most of it was radiated in the last 200 milliseconds. So in 200 milliseconds, basically 3 solar masses went poof into gravitational waves. You can convert that to a power. And the peak power, peak luminosity from this event is 3 times 10 to the 56 ergs per second. To put that number in perspective, that is about 50 times the total luminosity of the visible universe at any given time. So this was a really catastrophic event that almost went unnoticed. All right. So it took us 5 months to write a paper, and I can tell you when you have 1,000 authors, writing a paper with 1,000 authors of something that's of this magnitude of discovery is no mean feat. And there were 6 people who basically dedicated 5 months of their lives to coordinate the writing of the paper, and they did a magnificent job. So the paper was published in PhysRev Letters on February 11th, and we had a press conference in Washington, D.C. The National Science Foundation was there, and these are just some pictures. The one I like is the one in the upper right where Ray Weiss and Kip Thorne, they're the 2 co-founders of LIGO. They've been working on this for 40 years. When they handed off their speaking duties to each other, they hugged each other, and that was quite a poignant moment. For me, what was more, and I think for most of us, what was more amazing was the reaction that this discovery got. And I would say that, first of all, the day after, there were, I think, 200 daily newspapers worldwide had this story somewhere in them, most of them on the front page, which was quite amazing. We made it into popular culture. This is a cartoon, basically a segment of a cartoon from The Guardian that I really like. Basically, you can say, it says, obviously we can't see these waves. The only way we know they're real is the extremely sensitive device which detects scientists having emotional feelings of excitement about them. All right, so that peak in the middle is gravitational wave discovery, and then the peak next to it is something called a cheese salad sandwich. I don't know what that is, but apparently it's something that elicits emotional reactions in scientists. The fun fact, which is totally wrong, I can tell you, is scientists' emotional reactions are also the equivalent of the width of a proton, the fractional width of a proton. I can tell you that when we discovered this, we were pretty over the moon. Turns out you can now buy gravitational wave fashions, all right? And if you look at my tie, you'll see that my tie has the gravitational waveform GW14 or 150914 on it. Rebecca Anderson, sitting in the front row here, has that dress on it that I'm sure she'll be happy to show you. And this is actually very nice. This company is called Shinova. It's here in the Bay Area. And the person who runs the company basically is trying to promote women in STEM careers, and so she designs these dresses, and now she's doing ties. She designs these dresses for interesting scientific things, so you can buy integrated circuits and things like that. So I thought that was really, really quite cool. And she found out that I was interested in a tie, so she made me a tie. That was nice. I think you can buy it now. One of my favorites, this showed up in New York City in, I think, March or April. All right, you go in the New York City Metro, and it says, scientists have found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet. All right, ad campaigns, I don't know. This gentleman is a swimmer from Australia. He is the world champion 100-meter freestylist. Cameron McAvoy is his name. And he loves gravitational waves so much that he put them on his bathing cap. All right, I think, and I'll let you guys be the judge of whether or not this is a cultural sort of touchstone, but I knew we'd hit it big when I saw that. Okay, all right. So this is all well and good. What comes next? Well, we hope we're going to see more gravitational waves. We still have a data set that's being analyzed, and we'll be releasing results from that hopefully in the next month or so. But in the meantime, we want to do better. And so we have plans for making our detectors even better. And you might wonder how you can make them better. These measurements are really hard. And so the way you make them better, and this is a progression of sort of how we expect this to go, is that you can employ techniques to get around radiation pressure and get around shot noise using something called frequency-dependent squeezing, which I suspect some of you in the audience are familiar with. And so these are sort of our goals for how we're going to progress in our sensitivity for the next, say, 5 to 6 years. And what's really important there is the numbers. You might not be able to read them. They're ranges to different kinds of sources, binary neutron stars, binary black holes. The range that we can see, all right, it determines the rate, but it determines the rate in a volumetric way. In other words, if we double the distance that we can see to a source, we increase the rate because we increase the volume by 8 times. So if we're seeing, for example, one event every 2 months with initial LIGO as it is right now, when we get to these curves that are in the bottom, you know, that cyan curve at the bottom there, we'll be seeing events 2 or 3 times a day, all right? So that just tells you, all right, how this field can progress. We'll become really an observatory very, very soon. All right, but in order to make those improvements, we don't have to beat just shot noise. We have to beat the coding thermal noise, and that's a tough one. Let me talk a little bit about the gravitational wave network, and then I'll come back to squeezing. All right. One of the things that's very important to recognize about interferometers is that they're very poor locators of sources. In other words, a gravitational wave that comes in from any direction almost any direction, will record a signal on the interferometer, although there is a radiation pattern. So it's more like a microphone, less like a telescope, if you will. All right, so in order to get directional information, you want to have a network. So we have our 2 LIGO detectors in the United States. There's a detector in Germany, GEO600, not sensitive enough to really make a contribution going forward. It's a great detector for prototyping some of the technologies that we use. There's a detector under development outside of Pisa, Italy, called Virgo, comparable to LIGO. There's a detector under construction in the Kamioka Mountains near the Super K neutrino observatory called CAGRA. Again, going to be comparable to LIGO. And just about 3 months ago, not long after the detection, the government of India, the Indian Prime Minister, announced that we're going to be building a clone of the LIGO detector in India. And why India? It turns out India is actually a very good place to basically fill out the global network. In other words, what you're trying to do here is have multiple detectors see the signal. Because you get the time information from the phase of the wave, all right, you get timing information, much like you do when you triangulate. So here you're n-angulating. And that gives you much better localization, and I'll show you that right now. So this is actually another nice picture from our discovery. This is a probable location of the black holes looking at the night sky. You see the Milky Way galaxy there. You see the Large Magellanic Cloud, which is where that banana sits. There's a little bit of an island off that banana. That localization pattern is what you'd expect to get for a two-detector detection, Hanford and Livingston. All right. What you really want to do, though, is make that much smaller. So that the area under that curve there is about, I think, 600 or 700 square degrees. And if you're a telescope and you want to search that and you want to do it in one night because you want to find an electromagnetic counterpart, in other words, the black holes that we saw didn't produce any light, but maybe binary neutron stars do. In fact, we believe they do when they collide. All right, if you can see those, all right, in gravitational waves and E&M, you've got a really great story to tell. And so that's really one of the holy grails of LIGO going forward. But in order to make it work really well, you want to shrink that error box, that banana. And so you can do that. And this is a simulation that we did basically with our black hole discovery. Again, they shouldn't emit, but let's just use that as an example because we have it as real data. All right, if you look at the plot on the right, you'll see the banana. All right, I've simplified the banana there. And there's a little dot in the center. And that little dot in the center is actually the improved localization that you get by bringing the two LIGO detectors, Virgo and India, online. It doesn't even include Kagra. All right, and the area of that banana goes from 375 degrees to 7.8 degrees, which is an area in the sky that an astronomer can work with. So our goal here is to get these interferometers running. They'll be running over the next few years. Virgo will come on next year, Kagra 2020, India 2023, and be able to do these multi-messenger astronomies. All right, quickly coming to the end of my talk, squeezing and shot noise. I think, again, people here might be familiar with this, but how do you beat shot noise? How do you beat radiation pressure noise? And the answer is you squeeze it. Light is a quantum beast. All right, so if you think about an electromagnetic field, all right, it has an amplitude and a phase, but the amplitude and the phase are basically, because they're quantum, they're not well defined. So in the best case, with no squeezing, you have this coherent state where that ball that sits at the end of that electric field vector has an area that's defined by the Heisenberg uncertainty principle. But there were a lot of good work done in the 80s, both theoretically and experimentally, that showed that you can manipulate that quantum state by squeezing it in one quadrature at the expense of the other. So you can squeeze it in phase, all right, that's shown with one of the arrows, or you could squeeze it in amplitude, all right? And so the way you do that is you inject, you squeeze light using optical parametric amplification, all right? And you inject it into the dark port of your interferometer because that's where actually the vacuum noise fluctuations come in. So even if there's no light, there's still vacuum fluctuations, but you get rid of it by injecting the squeezed light. All right, and that simple diagram shows the signal. And we did that, and it was done first at Geo 600 back in 2011, and you can see their shot noise improved by about 3.5 dB. And then we tried it on the LIGO Hanford detector, actually between the construction, the end of initial LIGO and the construction of advanced LIGO, and we didn't do quite that good, but we still did quite well. We did 2.1 dB, and again, that sensitivity increase really helps you with the rate. All right, but the problem, of course, and you realize it as I'm talking, is that if you're squeezing the light in phase, you're taking a big hit in amplitude because you're making that ellipse much longer in amplitude, so there's much more noise injected into the amplitude fluctuation, the anti-squeeze port. But it turns out you can get around that, all right? And you can get around that with frequency-dependent squeezing. And this was something that was proposed, I think, in 2001 by Jeff Kimball at Caltech. Also, Kip Thorne was involved in that and some others. But it was first demonstrated actually just last year by colleagues of ours at MIT. And what you do is you run the light through a filter cavity. So you take your squeeze state, all right, which is squeezed in phase, and then you run it through a filter cavity that has the right pole frequency. In other words, the right frequency where the phase angle rotates. And if you do that, you can actually show that you can improve, basically get sub-shot noise limited performance, not only in amplitude, but also in phase. And so this is something that we're really excited about, and we're going to deploy probably in the next few years on Hanford, but we still have to get those coatings working here. So let me close at the end by saying that LIGO is only the beginning. Tomorrow there's going to be a very interesting announcement by the LISA Pathfinder team on some of their results trying to make these kinds of measurements in space. Not a gravitational wave detector, but basically trying to make displacements in space. And by doing that, you can actually see a whole new spectrum of gravitational waves, supermassive black holes. You can go further and use something called pulsar timing. And that allows you actually to look for really ultramassive black holes that sits in the center of galaxies. And then ultimately you could look for these gravitational waves from the Big Bang. And those we use basically very, very sensitive bolometers to do that. So there's a whole spectrum of gravitational waves, just like there's a whole spectrum of electromagnetic waves that's just waiting for us to be discovered. So it's really kind of exciting. So this isn't the end of my talk. I think it's the beginning in the sense that we've done something I think which is really cool. We've detected gravitational waves, and we've actually measured their amplitude and phase for the first time. We've seen a binary black hole system merge, so the death of two black holes and the formation of a new black hole. We're going to keep running and improving our detectors, so we should be able to do this more and more over the course of the next years, and we'll upgrade and even do a little bit better. So this is really the dawn of gravitational wave physics and astronomy. Let me thank again the people that did the work, the LIGO Scientific Collaboration. There are, I don't know, 80 logos there. Your university might be on some of those. There's also the Virgo Collaboration, about 250 people that we work closely with. And I will thank you, and I also point out before I step off the stage that there will be a series of talks on Thursday by a number of experts from LIGO, talking more in detail about how LIGO works and what the discovery was about. So I hope if you're around on Thursday that you'll see that. So I think I will stop there, and thank you.